Man has been melting and casting iron since the days of ancient Mesopotamia, but it was the Chinese in the 6th century BC who first achieved something approaching commercial production. Output was not limited to ceremonial statues, but included everyday items like this rice bowl. The art was lost and rediscovered several times by the medieval Europeans, and during the Middle Ages, iron was a luxury item. Edward III even included the kitchen pots and skillets in the inventory of the Royal Jewel Collection. By 1644, production was back to normal, and cast iron pipe was used to supply water for the fountains of Versailles. The builder, Louis XIV, emblazoned his initials on the pipe, and present-day visitors to the palace can see the same pipe still in service, providing the brilliant aquatic display, a tribute to the corrosion resistance of this metal. When the Pilgrims came to America, they brought with them the English knowledge of casting, and an iron foundry was constructed at Saugus, Massachusetts, the second industrial plant to be built in America. Soon it was busy turning out the cooking pots and farm tools so essential to the survival and growth of the colonies. Technological revolution followed fast upon the heels of political revolution. Charcoal was being replaced by high-grade foundry coke as the fuel to melt the iron, and a new, more efficient furnace, known as the drop-bottom cupola, was introduced. But in spite of these improvements in the method of production, the basic properties of cast iron had changed very little from the days of the Chu dynasty. While it was a most useful metal, it did have limitations. It was heavy, had a low tensile strength. Once broken, it was difficult to repair. Modern cast iron has overcome these limitations, not only by changing, but by growing into a whole family of different irons. Irons which are being used in applications undreamed of 50 years ago. To understand how all these irons differ from one another and from steel, their sister metal, let's begin with chemically pure iron. Adding as little as 1 part per 1,000 of carbon converts the iron into steel. This is the soft sheet steel used for drawing and forming. To produce an easily welded mild steel, such as for structural beams and plates, increase the carbon content to 2 or 0.3%. When responsiveness to heat treatment is required, such as for forging steels, 4 to 0.5% is used. 6 to 0.7 carbon produces tough rail steels. Above 1% carbon content, the ability to hold an edge becomes dominant, and such steels are used for razor blades. Above this carbon content, the various cast irons begin. But cast irons differ from steels in that they must contain silicon. This third element, like adding a third dimension, makes cast iron a ternary alloy, more complex than the binary alloy, steel. And complex is the word, because strangely enough, entirely different types of iron can be produced from molten metal of essentially the same basic chemical analysis. Here's what happens. As much as 6% of carbon can be dissolved in iron when it is molten, but less than 2% can remain combined with the iron after it solidifies. What happens to the excess carbon that is not in chemical combination with the iron determines the type of cast iron produced. This can best be seen under the microscope. Unlike other metals, the 5 different cast irons cannot be distinguished by their chemical composition alone, but by differences in their microstructure. This, for example, is the microstructure of white iron. The excess carbon is present as hard, brittle iron carbides, which dominate the structure and make white iron hard and brittle. This makes it especially good for severe wear applications, like the tread rollers on this bulldozer. By subjecting certain types of white iron to a special heat treatment, the iron carbides break down into iron and carbon. After a day or more of this treatment, the carbon actually moves through the solid iron to collect in little gobs or nodules of graphite. Iron with this microstructure is called malleable, and its properties are opposite to those of the white iron from which it is derived. Rather than being hard and brittle, it is easily machinable and well able to withstand sudden shock without breaking. This makes it excellent for tools which may be subjected to severe overloading. The greatest volume of cast iron produced is gray iron. Here the carbon forms into graphite flakes during, rather than after, solidification, reducing solidification shrinkage and creating sound castings, no matter how complex. Other properties, such as machinability and strength, help to make modern gray iron the logical material for many products. Born with a spectacular display, ductile iron is the newest member of the cast iron family and is produced by adding trace amounts of magnesium to the molten metal. This alters the surface tension, and the graphite flakes group themselves into spheres, giving ductile iron unusual characteristics. The most remarkable of these is ductility, the ability to be bent or twisted without breaking, hence the name by which this metal is popularly called. Even more important, however, is the fact that ductile iron is produced with tensile strengths as high as 120,000 pounds per square inch. This puts it in the same tensile range as steel, yet with the castability and machinability of iron. Thus, this type of cast iron is finding applications in the exotic missiles and rockets field, an area long considered too demanding for any of the older metals. To meet the needs of industrial applications calling for resistance to corrosive atmospheres or high temperatures, cast irons can be alloyed with nickel, chromium, molybdenum, or copper to produce an endless variety of special property metals needed to meet any unusual requirements. So much for the metallurgy of cast iron. But how do you make it? How do you go about converting this into this? How are last year's discards transformed into new and valuable products? The magic starts with the basic raw materials. Iron ore is processed into pig iron. And coal is transformed into special metallurgical coke. The production of cast iron now begins. A layer of coke is charged into the cupola furnace and set on fire. This not only provides the high heat for melting, but also the carbon needed for alloying. At the same time, limestone is added as a flux to remove impurities. Then the basic raw materials, pig iron, selected scrap iron, and scrap steel. The proportion is determined by the type of iron desired. Then another layer of coke and limestone, followed by more pig iron and scrap. This layering process continues until the cupola has received its proper charge. As the metal melts, a pool of molten iron collects at the bottom of the cupola, where it is tapped into large ladles. The impurities are withdrawn at the other side in the form of slag. As the melting proceeds, more raw materials are charged at the top, so that the process is continuous. Thus are the raw materials converted into a smooth flowing stream of iron, a stream whose chief value arises from its ability to take any desired form or shape. The method used to cast the iron into the desired shape depends upon many factors. These include the size of the casting, number of pieces needed, degree of finish required, and intricacy of design. As an example of the principles involved in all methods, here is a typical casting, and this is how it might be produced by the most common method, green sand molding. First, a copy or pattern is made which conforms to the external shape of the casting. This will be used to form a cavity in the sand. The mold is made in an open frame called a flask, and both the flask and the pattern are cut in two. Starting with the lower half, the pattern seen here in cross-section is placed flat side down on a board, and the lower half of the flask put around it. Moist or green sand is now rammed firmly around the pattern. The flask is turned over. A dry parting powder is dusted over the bottom half of the mold. The top half of the pattern is placed on the bottom half, and the other half of the flask is locked in place. Perfect registration of both pattern and flask is assured by pins between the two halves of each. Now more sand is rammed into the flask, and a hole is cut to form a passageway for the molten metal. Then the two halves of the flask are parted to remove the pattern. A channel is cut in one of the parting faces through which the molten metal will be fed to the mold cavity. The reason for the black extensions on the pattern now becomes evident. The inside surfaces of the casting are formed by the core, made of hard, dry sand, which keeps the molten iron from completely filling the mold cavity. When the core is placed in the mold, it is supported at the ends by the depressions in the sand made by these pattern extensions. Now the mold can be closed and the iron poured. After the molten iron has hardened, it is dumped from the mold. The core has disintegrated and is shaken out, and the casting is now ready for finishing operations. The principles apparent in green sand molding are employed in all casting techniques, although most foundry production is now accomplished by mechanized equipment, like this jolt squeeze machine. The pattern is mounted on two sides of a board and placed between the empty halves of the flask. The operator releases the sand from an overhead hopper into the flask, and the assembly is then jolted to compact the sand. After striking off the excess sand, the bottom board is placed on the flask and the whole unit rolled over, exposing the other half. The sand filling operation is repeated, and then both halves are squeezed simultaneously. After squeezing, the operator draws out the pattern and sets the cores in place. When reclosed, the mold is ready for pouring. Another mechanized method of molding is the sand slinger, which throws a high-velocity stream of sand, filling the flask and compacting the sand at the same time. Large flasks can be filled quickly, which is one of the reasons it is used extensively in the next major casting method, dry sand molding. The pressure and erosion of large amounts of molten iron would be too much for green sand to resist. So the sand is coated and baked to develop the necessary strength. Dry sand molding is used primarily for the production of large, heavy castings like this rotating base for a radar antenna. One of the most exciting developments in the foundry industry is the shell molding process. Shell molding starts with a special metal pattern which is sprayed with a compound to prevent sticking and is then heated. This is clamped to a dump box containing an extremely fine sand which has been mixed with a thermosetting plastic resin. The box and pattern are inverted to bring the resin-coated sand into contact with the hot pattern. After about 30 seconds, the resin melts and forms a thin shell of bonded sand on the pattern. Upon righting the box, the excess sand drops away. And after a short curing time, the shell can be lifted or stripped from the pattern by built-in ejector pins. Two mold halves are pasted together with resin glue and the pouring can begin. Shell molding which produced these gears permits extremely close control of both surface finish and dimensional tolerances. Thus, finishing operations such as machining and grinding can often be eliminated. Castings of unusual complexity, like this air-cooled engine cylinder with very deep, thin fins, are often produced in a mold made from the very fine sand used for cores. This is known as core mold casting. This sand has almost free-flowing properties, and when it is packed around the pattern, it will fill every crevice and reproduce very fine detail. It is then baked to develop its strength. The fifth major method of iron casting is permanent mold. As the name implies, the molds are permanent, made of gray iron. The process begins here with this acetylene flame which deposits lamp black on the mold to prevent the casting from sticking. The cores, if any, are then set. And an indexing device closes the molds as they move to the pouring station. The castings cool as the merry-go-round rotates, the cooling rate controlled by large volumes of air blown over these cooling pins built into the back of each mold. The red-hot castings are ejected and the mold returns to the acetylene lamp blacking station to repeat the cycle. For large volume production, such as that demanded by the automotive industry, permanent mold casting is highly efficient. Other molding methods include such specialties as ceramic molding, here being used to produce the vulcanizing molds for tires. Investment or lost wax casting, once confined to precious metals, but now coming into greater use because of the demands of the aerospace industry. Centrifugal casting, used to produce seamless pipe. And continuous casting for the production of cast bar and rod stock. This parade of new production techniques and new types of iron has never stopped. Now, some 300 years since the building of the first American foundry, the universal acceptance of cast iron stems from its many and varied properties, some of which cannot be duplicated in any other material. These properties make it the logical choice for many, many applications. Getting up on those cold mornings isn't so bad when you know that you can warm up the room quickly thanks to an efficient heating plant. Cast iron is an excellent heat exchanger, providing an even flow of warmth. Cast iron pipe has been a favorite of water and sanitary engineers for centuries because of its resistance to corrosion. Your automobile power plant is over 90% cast iron. The high fluidity of molten iron makes it possible to cast the intricate passageways of the water-jacketed block and head with complete soundness, while the wear resistance and built-in lubrication effect of the graphite extend the life of the cylinder walls. A little-known property of cast iron is that its compressive strength is 3 to 5 times greater than its tensile strength. This makes it ideal for applications such as this bridge, where the rockers, rollers, and bearing plates must stand the continuous loading of rush hour traffic. Freon, a gas commonly used in air conditioners, is one of the most pervasive of all elements. It can seep through the most minute crack. Air conditioning and refrigeration compressors cast of iron are completely sound and gas-tight. And with so many milling and drilling operations to be performed on the average compressor, the free machining properties of iron are invaluable. One of gray iron's many unique properties, its damping capacity, finds application in the piano. Damping is the ability of a material to absorb vibration and control sound. In the piano, the strings are strung on a frame cast of gray iron. The damping effect of this frame prevents the after ringing, which would destroy the artistic effect of many musical passages. This same property makes gray iron a logical choice for the bases of heavy machine tools. Factories would be unbearably noisy, and the accuracy of the tools would be thrown off without the damping effect of the cast iron components. 2,500 years and the rise and fall of a dozen civilizations separate the early uses of iron from the highly sophisticated applications of iron castings in today's technology. No one can predict what new uses and applications the future will bring. For while the biography of a man always comes to an end, the biography of a metal goes on forever. These next pages are being written by America's foundry industry, where the fires of creativity burn late into the night.